me, but today it will be given by my assistant, Bob Gilman, director of Algebra and Cryptography Center at Stevens Institute.
Wait, do I need to speak into this? Oh, okay, excellent. Okay, group theoretic cryptology. What is that? So if I learn how to use this, there. It's something Gilbert was interested in and Ben was also interested in. So that's they have 3 different articles as far as I can tell, maybe more, I'm not sure. These are what I could find. And they're all about public key cryptography. And I'll explain what that is and what it has to do with groups. So, okay. Now, okay, so the public key cryptography comes first. And this is a very, there are several experts in the audience. And I asked them to bear with me because this is I'm not assuming any knowledge of cryptography on the part of any of you. But you all know that cryptography is important for protecting data on the internet. And we can imagine this. Oh, let's see if this works. This here. This is maybe the communications channel here, might be the internet. And Bob here wants to send a message to Alice. And Eve is the eavesdropper. She's just listening to everything that she can. So, you take your card and you put it in a, you want to withdraw money from your account, you put it in an ATM. The ATM sends messages over unsecured phone lines and to your bank to find out whether you actually have any money. And then it dispenses money if you have enough to dispense. And someone who's eavesdropping could just repeat that. So you want to make sure that that can't happen. So you encrypt various things so that Eve won't get any benefit out of this. Now, the way encryption works, we all know there's a sort of an algorithm for encrypting, and you have a secret key. The usual way of thinking about these things in terms of security is that your enemy, Eve, and maybe even more malign enemies, know everything except all details except for the secret codes, the passwords, whatever you want to call them. So password, secret key, I guess is what you call them. So Bob has a secret key, and for this algorithm, he uses that secret key to encode, sends the across, and then Alice has to use the secret key. Usually it's the same secret key, it's for convenience, to decode. But even if it's not the same secret key, she has to know what it is. So how does Bob arrange to send the secret key to Alice? You're trying to send a message to Alice using encryption, but you have to send the secret key to Alice using encryption. And luckily, it turns out that you don't have to do that. Alice can publish what's called a public key, and so that anyone can send her a message. This is asymmetric cryptography. It's something that was discovered in the 70s by people who were not behind a security wall, and in the 60s by some British crypto people who weren't allowed to say anything about it. Maybe 70s and 80s, 60s and 70s, something like that. They couldn't, the crypto people couldn't think up any practical applications. So anyhow, so Alice publishes her secret key. She publishes her public key, and then Bob uses that to encrypt something, and then Alice uses her secret key corresponding to her public key to decrypt. And I'm going to review the first kind of way that this was done, the so-called Diffie-Hellman protocol. By the way, there are lots of, in implementing this has nothing to do with practical implementation, or it has very little to do, because there are lots of practical problems in actual implementation. So this is kind of an overview from the point of view of people interested in the math that's going on. And so much trouble to take a look. Yes, right. And in fact, it's very, another thing that I should say is this public key is crucial because not only can you distribute these, we've solved this problem of secret keys, you can use this to distribute a secret key to some other encryption, decryption using what's called symmetric cryptography, where so you can, the public key systems are very useful for this kind of initial, when you're transmitting a small amount of data, but they're very slow. And usually you want to transmit tremendous amounts of data. So you're using different crypto setup for that with this called symmetric, and each person needs a secret key, and that you can distribute using public key cryptography. Okay, have I sufficiently confused things? So let's the first sort of public key system was based on modular arithmetic. So you'll notice a group was involved. And so, all right, so you pick a finite cyclic group. Let's forget about, usually everything is presented, the cyclic group is presented this way, and you're using modular arithmetic. But for the group, from the group theory point of view, how am I going to use this group? I publish a cyclic group, G, and I publish, Alice picks her secret key, and then she creates her public key is just this element G, which is the generator of my cyclic group. You just raise that element G to the power 3 that Alice has picked. And you get, in terms of modular arithmetic, you do this and you get that. So it's Alice's public key. Of course, in practice, instead of the prime 23, when the primes typically have hundreds or even thousands of digits in them. Okay, and Bob does the same thing. So Bob's private key is 4, and Bob's public key, well, turns out to be 4 too. That never happens in practice. But anyhow, so how does this work then? What's the secret? They share a secret. The secret is that Alice takes this Bob's public key. This is Bob's public key is this, and Alice raises it to her secret key. So she gets just, the arithmetic is just G to the BA. And Bob does the corresponding thing and gets G to the AB. And because that's supposed to be an equal sign in there, that's the same thing. So they've managed to compute to share a secret. The secret is 18, as congruence class, mod 23. And well, what about Eve? Eve knows everything that's public here. So Eve, to break the crypto system, the sort of straightforward approach by Eve is to try and find the secret keys. If Eve can find the secret key, then she can use exactly. Eve knows everything in here except for the secret keys, so she can do everything if she can find A or B. It doesn't matter. That's called the discrete log problem. So, what is what? What is that? Yeah. This should be the subgroup and its generator. These are public. So Eve knows this thing, which is actually just this setup right here. I guess she knows this. She also knows G to the B, if it'll help. And from that, compute the discrete log problem. Solve the discrete log problem. That's a straightforward way of trying to break this crypto system. And of course, in practice, P is very large, and it can't be just any prime. It has to have certain properties, satisfy certain properties, and so on. So also, this system is no longer valid. This was actually used, again, with all the actual practical details added onto it. But this is no longer secure because of quantum computers. Quantum computers can, in fact, solve the discrete log problem. And they quantum computers were always 20 years in the future, except now they've been built. And they're not quite big enough to solve, at least as far as I know, in the discrete log problem for groups of the size that are used in this, in practical implementations of Diffie-Hellman. But they're going to get bigger, and so that's why there's a frantic race going on to replace Diffie-Hellman with something that is post-quantum, something that's resistant to quantum computers. Okay, so that was the first. That's a public key system that was actually used and worked and also involved a group. But one of the things this led to, so this was, we're talking, started, I think, in the 70s, people. This was invented, 76, I think. And the algebra that goes on applies, basically, can apply with a change, which I'll mention in a minute, to any group. You don't have to take this group right here. And particularly once it was noticed that Diffie-Hellman was no longer secure, people began to try and find other groups also that to find something that looks sort of like this algebraically. You don't need to be doing exponentiation. You can do conjugation. And so let's see if I can remember how that, oh, well, all right. All right, so one of the first, there are two, the Coley and Anchel-Goldfeld. I'll talk about Coley and then just mention a little bit Anchel-Goldfeld, but here's where groups come into play. And it works exactly the same way, except that you take a group, and since exponentiation is commutative, that was very important. G to the AB is the same as G to the BA. So you need a group with two commuting subgroups. And then the private key is in one, and the public key, again, you have this G. It doesn't have to be a generator anymore. It's just a public element. So your group is public. This is public. And Alice's private key is just some group element in this subgroup. And if her public key is a group, the element G conjugated by W. So that's just this. And Bob has, again, a private key in the commuting subgroup, and the public key, his public key is formed in the same way. And then we just do the same computation we did before, that the shared secret, well, you're dealing in a group here, but basically Alice, what is Alice? Alice has, this is Alice's public key and Bob's secret key. So Bob does this computation right here, and Alice does this computation right here. And because W and V commute, this is the secret is the same. So again, so they've shared a secret. Now they've shared a secret. Now they can use that with some very fast symmetric crypto system. So we don't need all this public key stuff. Okay, Anchel-Goldfeld, which I think maybe this was another one that made quite an impression, because it's something you can do in non-commutative groups that you can't do in commutative groups. So here, Bob just picks a private word over some elements which are public. So you publicize nothing about commuting between A and B. A and B are just elements of the group. The group is public, and the A's and the B's are public, and the secret key of Alice is a word over the A's, and the secret key, right, and a secret key for Bob is another word, and the public key is the Alice is the AI's conjugated by, so Bob takes, this is public, but this is and this one is public, but this one is secret. So, but the conjugates are public. So so here, Alice, this is Alice's secret key. This is what she publicizes. She sends this to Bob, and so on. And then the computation goes the way it did before. Alice computes x to the y, because if you what can Alice do? Alice computes x to the y. Alice knows x, and why can she conjugate it y? Because she builds it from these I've got this backwards, but anyhow, yes, Bob sends these conjugates. From these conjugates, since Alice's word comes over from here, from these conjugates, Alice can construct x to the y. Thank you. And then she can also compute x inverse x to the y and get this commutator. And Bob does something similar and also gets the commutator. So they're commuting, they're both the shared secret. Okay, so this is the way sorry, this is the way that public key cryptography works. And there was a lot of interest, which has continued until this day, in trying to find, implement this or one of these two or something similar. A lot of different algorithms or crypto systems were proposed, and one wanted to construct one that was immune to quantum computers. Now, the way to, so this is based on the security of this system means that Eve, with the information that we have here, what the public information, should not be able to solve to compute the private words, private keys. And so trying to find the X from B's and BI. So Eve knows all of this public stuff. So she knows what the B's are, and she knows what their conjugates are. So there's a whole bunch of things, and underneath them, you can put all their conjugates. And from that, you can try and guess the conjugating element. That's the routine sort of that has to be secure. So if that's not secure, then AAG is not secure. And so there is this sort of algebraic problem on which the security of AAG rests. Now, there are a lot of other problems that AAG has that are well, before we get to that, maybe. So the conjugacy search problem is the crypto primitive, an algebraic problem involving groups. It's a crypto primitive on which this crypto system is based. And there are many different variations. The original AAG, I think, is a little bit difficult because the security of an actual system depends upon specifying very many parameters. And so we haven't done that here. So we're really talking about just the idea of a system. But I think, and I may defer to the experts, that AAG is sort of believed to be not reliable, or at least AAG with certain, based on certain groups. Yes, yes, and that there are many other attacks. I mean, one attack. So what we're interested in is sort of as a mathematical problem is what is the security here? What's going on? And the one way is to just attack the crypto primitive, the problem on which the crypto system is based. There are many other attacks also, and I'm not going to go over all of them. In the last, 20 or 30 years, it's gone back and forth. I'll just mention that, well, with regard to Diffie-Hellman, the original Diffie-Hellman, this variation on it was posed as a post-quantum, that's a post-quantum, a secure post-quantum crypto system, and it passed several tests. The National Institute of, what is it, NIST, whatever that is conducting a search for what's going to be our next sort of crypto systems that we're going to use. I mean, to secure the internet. And it takes about 20 years to set up the actual system once you've decided on it. And by that time, I'm pretty sure there'll be quantum computers that are big enough to break Diffie-Hellman and other. No, it's a variation on Diffie-Hellman that actually by other people. Yes. Yeah, not by Diffie and Hellman. And yeah, so there have been lots of sort of people try to make Diffie-Hellman. It's such a nice sort of clean way to do things. And anyhow, whatever it is, it was thought to be immune to quantum cryptanalysis or quantum computers, and it was only recently broken after passing several layers in July, I think. And but people are still working on Diffie-Hellman. So Romankov Vitaly has recently published an improved version of Diffie-Hellman. That's the way it usually is with these things. The crypto system is published, and then it's broken, and then it's revised, and then it's published again. And eventually it either disappears or maybe it becomes accepted. Anyhow, so I'm skipping all these sort of many variations and attacks. But if you're interested in pursuing this, I'm going to talk more about security, sort of the mathematical aspects of this in a minute. But here's some references. This is, of course, is Vitaly's article that he just published. And this is a paper with 10 authors, many of whom, what? A book. Yes, it says book, doesn't it? It says book right there. A book with 10 authors. And many of whom are in the audience. So, this is an earlier sort of review from a little bit earlier. But it's addressed specifically to mathematicians. So if it's something you're interested in, you might want to read that one too. Okay. Oh, by the way, how much time do I have? Sorry. I forgot. I'm not sure how long this talk is supposed to be. Oh, okay. When did I start? Right, but I mean, I was supposed to start at oh, wait, I've already finished. Okay, thank you. All right, all right, cryptanalysis of public key systems. All right, that's let me go on. We don't know how to do this. There are many other attacks. So the first attack on a crypto system is to try and defeat the crypto primitive. The second attack is it can be all kinds of things. If the group that you're using, suppose we're trying to find a right group that'll work with Diffie-Hellman, and if that group has a linear representation, you're probably out of luck because you can use linear algebra. And there are other things. This algorithm, Diffie-Hellman, involves choosing elements at random. And for a group, we don't have access to the elements of the group directly. Usually we have a set of generators, and we look at all words over their generators. And so to pick a random element, we pick a random word. And you can, turns out that for some groups, like a braid group, if you pick a random word by just picking as thank you. As Ilya suggested, you just get something with the subgroup you get that's generated by that word is extremely likely to be free in the braid group. And that gives you an advantage that the people who invented the system were not aware of at the time. So there's a lot of sort of group theory that goes into that. And this is where things are in regard to security. We don't know very much about security, but what we do know, do I really only have 2 minutes? Well, all right. All right, so Ilya kind of alluded to this in his talk. So I don't, this is just we want to find out, our cryptos are crypto primitive should be very hard to solve in almost all the time. But that's important. and almost all the time is mean it's very it's solvable only on a negligible set of elements, easily solvable. That's what you want for this. And we define that, and this is already subject to not everyone accepts this, but it's sort of the logical thing to do using what we have at hand. So X is generic if these densities, you have a finite alphabet. The alphabet, words in the alphabet represent words in the group, and the alphabet is divided into all words of length n, and you take any set X and you form of all the words of length n, the percentage of words of length n. If that percentage goes to 1, I mean the percentage of words of length n which are in X, if that goes to 1, then X is generic. If it goes to 1 very fast, then X is exponentially generic. So it's just a concept of what so you can prove a lemma, which then the set of all words not divisible by a fixed word is exponentially negligible. So that's something that is easy to prove, and you can use that to try and say something about security. So what I'm going to say is, just briefly now, that supposing we have a map from a free monoid over some finite alphabet to another free monoid, and we want to compute some function. And I'm going to talk about an easy case, but you can also do this and get a weaker conclusion for if you just assume, for example, that F is, instead of being uncomputable, that doesn't have that much relevance. Assume that F is does not work in exponential time. Then you can get some also statement, which I'm not going to present, but which is maybe more relevant to the problem at hand. Oops. Okay.
What does the hash indicate?
Sorry?
What's the hash sign, the pound sign? What's the...
Oh, that's just an extra character. All right, so here's what I want to do. I have a function, and suppose I'm trying to compute this function, and in this theorem, suppose this function is not computable. Now, functions which are not computable are often computable almost all the time. So if we're trying to use a function for something, we would like it to be not computable. We'd really like it. Not computable is not actually applicable to the crypto problem, but rather it would be not in some computability class. But to get going, let's assume it's not computable. So this function is not computable, but it may be only, well, if it's not computable, it has to be not computable. If you take an algorithm, that algorithm must fail somewhere. Well, we can add that to a list of special instances. So algorithm must fail infinitely often. Any algorithm to compute this function fails infinitely often. And so then let's try and make it harder to define. Basically, this function maps words here to words here. So just add another element like this, and then I can, elements in this, the words over this alphabet look like this, and then I can define a function that by just taking this function and evaluating here and here and here like that, and get another function. And the point is, this function is uncomputable on a generic set, and an exponentially generic set. So so I've taken a function which is not computable on some undefined set, so at least some infinite set anyhow, and I've produced a function which is a different function, but it's not computable on, it's only computable on exponentially negligible sets. So I want to do the same thing, not with regard to incomputability, but with regard to functions which might be useful in terms of constructing cryptosystems. And there are results, but they're preliminary, and besides, I'm out of time. And this is the proof. The proof is very straightforward, and basically, suppose this function is not computable. So, and then look at this function. From any algorithm for this function, you can compute this by just taking this function x and evaluating it, if I evaluate this function, that involves computing all of these things. So if I compute this function anywhere where one of these w's is a w that I'm interested in, then I'll be able to that involves computing f here. And so, but the point is just that sort of straightforward change from here to here, because of this lemma on the preceding page. So the algorithm, take any algorithm for this, use an algorithm for this to evaluate this function by applying that algorithm to all words like this that contain a fixed word w. It's one of these things. So that's all words that are not, this algorithm must then fail. This algorithm just runs forever. You'd set it and keep applying it on all words that look like this and let m go to infinity. And then if it ever if it ever halts, then since this one of these words is by definition is the w in here, you're trying to compute f of w, then you've computed f of w. So but that can't work for all w's. There's some w here for which any algorithm must fail. So there's some w here such that this fails on everything that contains that word w with the special character at the beginning and the end. And so that's an exponentially negligible set. So all right, so I think I wasn't quite sure how long I was going to talk. I think I probably talked a little too long. But anyhow, so the point is here that this is I haven't seen this anywhere else, and I don't understand because it's so simple. And so but it seems to me, you can get some kind of results. So looking ahead to the results that I haven't actually presented yet, I'll ask the audience a question. So supposing you're trying to show that the conjugacy search problem on for the exponential Goldfeld, you have the conjugacy search problem on a bunch of a sequence of words. You could sort of code it in this way. So you could do this. If you have a conjugacy search problem that is, well, I mean, I don't want to say for sure about the conjugacy search problem, but you would it's kind of suggestive. I'll just leave it at that. But the question is, I have a group theoretic question for the audience, and that is there a group where the conjugacy search problem does not have exponential time, cannot be done in exponential time? Cannot.
You mean the worst?
Worst case.
Yeah, worst case, just worst case.
But there are undecidable.
Yeah, I know, but that's too hard.
What do you want? Decidable, but not in exponential time.
Yes.
Super.
Yeah, I guess that's the right way to phrase it.
I think you can.
Yeah, you can see. I've always wondered whether I mean, Diffie-Hellman with the brain group just didn't seem to be the right group for Diffie-Hellman.
With the there are artificial.
Yeah, there are. Word problem and one Turing degree context problem and the other.
But
I understand, but this.
You're talking about the group theory question.
Yeah, so I mean, in principle, such examples exist, but they are really artificially constructed.
Okay, all right. Anyhow, so that's.
Can you do something like that? Oh, sorry, we have the picture. Sorry.
Yes.
Or you are not quick.
Well, I asked you a question. Wait a minute. Now you're entitled to ask me questions.
Yeah.
No, I didn't make, these are all the slides that I made up. So
So with respect to this slide, can you start with uncomputable function?
right. You can,
Suppose you start with the f, which is not computable in exponential time.
right. Then you could get results. I'm not exactly sure what the optimal, yeah, you can.
But that would be better because
Yes, but you don't get exactly, you get some result but I haven't quite figured out how to formulate it. Here, what happens is when decidability, it doesn't matter. Sorry, in decidability, it doesn't matter if I'm for computability or decidability, it doesn't matter that it gets longer, but because I can, if this is anyhow, if this were just not exponential time, and I'm looking at these words that are getting longer and longer and longer, I'm allowing myself more and more time. And so from looking at this, and I have to be able to say if this is say if this is computable, then something, this is computable, and then otherwise, if this is computable in time, 2 to the length of this, then this must be computable in time, but 2 to the length of this could be very long. So I don't get a good estimate for complexity here, but I do get something. So, but it's not quite clear what it is. You do get, you can sort of get a weaker result. You can show that well, I haven't actually optimized what you can show, but you can show that this one is much harder than this one. There are a lot of cases if this is not exponential time at a certain point for one word, then this is not exponential time for lots of words. And I haven't quite formulated that, so I didn't make another slide.
No, I have a comment about quantum computers. So there is a person, I'm sorry, I don't remember his name. He made a bet. So he bets $2,050 that by the year 2050, no quantum computer will be able to factor a 2000-bit RSA modulus. And there are 3 people already who picked up on this bet. And one of them is Daniel Bernstein, a rather well-known cryptographer who works for NIST on their post-quantum standardization team. So if some of us live until 2050, it would be interesting to know who wins. So my money would be on this person's side that no quantum computer will be able to factor RSA modulus, but that's not just because the technology is too complicated, too complex, and expensive. It's just that because I think artificial intelligence will take over, and that it has more abilities to sort of break crypto systems than a quantum computer.
Really?
I think so, yeah.
Oh. Okay.
Yeah, by the year 2050, it will be released. Okay, anyway, let's thank Bob again.
Thank you.
And the next and last talk.